To the function series limit continuity and differentiability theorem, part 2. Now, this theorem is interesting, but the proof is rather boring, just like in part 1. Let's have a look. So, let functions un, where n is a natural number, be finite differentiable. Finite differentiable on some open interval AB. Right. And let, furthermore, we assume that there exists some point x0 in the interval such that the sum, or the series of uns at the point x0 converges. Right? And also, we have a second requirement, or rather third, that the series of the first derivatives of uns converge locally on AB. Then, the function f of x, well, I'll just put simply f, equal to the series iterating through 1 to infinity of un is well defined and differentiable. Right, the proof is use this theorem on the right hand side and everything will turn out just fine. Also observe that essentially these requirements are simply the requirements of this theorem, right? So by observing and using our mathematical skills, we can immediately see that these requirements, these assumptions of this theorem perfectly align with the assumptions of this theorem, of the limit derivative exchange theorem. So having met the assumptions of the limit derivative exchange theorem, it holds that, and we have that there exists some function f equal to the limit sk approaches infinity sk, such that, which is equal, of course, by definition, to the limit of the series at some given point. This function is differentiable and the series iterating through 1 to infinity of un at x converges locally, exactly as the theorem tells us, to f, right? And the series, as n approaches, or as n iterates through 1 to infinity of the first derivatives of un of x converge locally to f derivative, or f prime of x on the interval AB. As I've said, apply this theorem and we shall obtain this beautiful result at the cost of a boring proof, which is precisely what we wanted, minus the boring proof.